Did you know? The programs you write are never executed in the exact order you wrote them. That's right, even the simplest 2 lines of code like this. In a modern CPU, it may actually play out like this. The second line starts preparing for computation first, while the first line jumps the queue later, and the result of B might even be guessed ahead of time by the CPU. This out-of-order execution mechanism allows CPU performance to improve by tens of times compared to traditional sequential execution. Today, we're going to demystify this modern processor magic, out-of-order execution. Let's break down how CPUs that can process tens of billions of instructions per second achieve such high efficiency through underlying architectural optimizations. Imagine you're waiting in line to buy coffee. If you had to wait until the person in front of you fully finished ordering, paying, and receiving their drink before you could even take a step forward, that would be extremely inefficient. Traditional CPUs used an in-order execution model where instructions had to strictly follow the written order. If the previous instruction wasn't finished, the next one had to wait. This model was acceptable in early computing scenarios, but as CPU clock speeds increased and the gap with memory performance widened, serious efficiency bottlenecks emerged. Take this code on the screen. When the first load A instruction is waiting for memory, the next 2 instructions cannot execute, causing the CPU pipeline to stall and wasting significant computational resources. Later, engineers proposed a groundbreaking idea. Why must execution be strictly in order? Why not let the CPU execute whatever is ready first? Thus, the core design philosophy of modern CPUs was born instruction-level parallelism with out-of-order execution at its heart. The core logic is, if instructions have no data dependencies, their execution order can be rearranged to prioritize ready instructions. The key implementation of this idea is out-of-order execution. Out-of-order execution must follow 2 critical principles. Instructions can be executed out of order as long as there are no data dependencies. The final result must match that of sequential execution, architecturally transparent. Simply put, the order you write your code ensures logical correctness, but the CPU schedule's execution, however, is most efficient as long as the final result is correct. To achieve out-of-order execution, modern CPUs employ a sophisticated architecture involving instruction decoding, register renaming, scheduling, execution, and result reordering to ensure efficient parallel processing of instructions. Instruction decoding. The CPU first breaks down machine instructions into smaller micro-operations. Complex instructions are split into independent basic operations, making them easier to schedule and execute in parallel. For example, a seemingly simple instruction like add a value from memory to a register is split into 3 micro-operations: read data from memory, perform the addition, and store the result back. These split micro-operations can be scheduled independently, preventing a single complex instruction from blocking the entire execution flow. Register renaming. Register renaming is a key technique for enabling out-of-order execution. Its main purpose is to resolve false data dependencies, where 2 instructions appear to conflict because they use the same architectural register but are actually independent, yet forced to execute sequentially. Inside the CPU, there are far more physical registers than architectural registers. Through register renaming, the CPU assigns each instruction an independent physical register copy, allowing seemingly conflicting instructions to execute in parallel. It's like this. The code only has 8 keys, but the CPU secretly prepares 200 keys inside, assigning a new one to each instruction. So instructions that appear to conflict are actually completely unrelated. The scheduler, the heart of out-of-order execution. Its workflow consists of 2 steps. Check the data dependency status of micro-operations. Determine if an instruction must wait for results from other instructions. Schedule ready instructions. Immediately allocate instructions with no dependencies to available execution ports. The scheduler follows a ready first principle, not strictly adhering to the original instruction order, ensuring the CPU's execution units remain highly utilized and avoiding idle resources. It's like handling tasks at a service counter. You don't wait rigidly in line. If a window is free and your documents are ready, you go straight there. The CPU never lets a core sit idle. Even if the previous task isn't done, it will schedule whatever work can proceed. Execution units. Modern CPUs integrate multiple independent execution units, each specialized to handle different types of instructions simultaneously. Common execution units include arithmetic logic units, multipliers, dividers, load, store units, branch units. Each execution unit operates independently, enabling true parallelism. Is an add instruction stalled? No problem. The CPU will find other instructions to keep working. Reorder buffer, the magic that ensures order. Out-of-order execution does not mean out-of-order completion. The ROB's key role is to reorder the results of out-of-order execution, ensuring they are written back in the same order as the original code. Execution can be out of order, but write back must be in order. This ensures programmers never notice the out-of-order execution. But out-of-order execution alone isn't enough. When faced with branch instructions like if-else, the CPU faces another dilemma. Which path should it execute? To address this, CPUs use branch predictors to guess the branch outcome based on historical data and speculatively execute instructions along the predicted path. If you have an if-else statement, the CPU will guess foo or bar even before the comparison is done and pre-execute many instructions. If the guess is correct, everything proceeds smoothly. If the guess is wrong, all computed results are discarded and the pipeline rolls back to the ROB. This is a pipeline flush due to branch misprediction. Fortunately, modern CPUs achieve prediction accuracy rates above 98%, so they guess correctly most of the time. Looking back at the 2 lines of code from the beginning, the CPU's actual execution steps are instruction decoding, split instruction 1 into load constant 1 and write to A's physical register. Split instruction 2 into read A's physical register, perform addition, and write to B's physical register. Register renaming, assign independent physical registers to A and B, avoiding conflicts with other instructions. Scheduler decision, instruction 1's load constant 1 has no dependencies, so it's scheduled immediately to an execution unit. Instruction 2's perform addition must wait for ES value, but preparatory steps like allocating compute resources can start early. Parallel execution, the execution unit handles instruction 1's load constant 1 and instruction 2's preparations simultaneously. Once instruction 1 completes writing back to A, instruction 2's addition and write to B are executed immediately. Result reordering, the ROB commits the results A equals 1 and B equals 3 to memory in the original order of instructions 1 and 2. The final result is identical to sequential execution, but by parallelizing preparatory work, the overall execution time is reduced. However, out-of-order execution isn't a silver bullet, it has limitations. First of all, real data dependencies cannot be optimized away. In the example, B must wait for A to finish. Next, heavy memory access can slow it down. No matter how smart the CPU is, it can't create data out of thin air. Thirdly, branch mispredictions cause significant performance penalties. A misprediction flushes the pipeline, discarding already executed instructions and rescheduling the correct branch, leading to major performance degradation. Finally, it introduces complexity and security risks. Out-of-order execution requires complex hardware support, increasing CPU design and manufacturing costs. Additionally, the combination of out-of-order execution and branch prediction can introduce security vulnerabilities, such as the Spectre attack, which exploits side-channel information from speculative execution to leak sensitive data. From this video, you should now understand why modern CPUs are incredibly fast. Modern CPUs resemble highly parallel task schedulers, more than the sequential code executing machines you might imagine. If you found today's content helpful for understanding performance optimization, compilers, or computer architecture, remember to follow for more. See you next time.